So thank you very much, Gianpaolo, and thank you very much for having invited me to give this keynote here in DAFx. Say yes, unfortunately I will be here only for one day, but it's a wonderful day, so I'm very happy to be here in DAFx. So my talk is in fact on hybrid deep learning for audio, and what I plan to discuss here today is first to give a bit of context and motivation for hybrid deep learning in audio, and then give some insight and some examples of what is hybrid deep learning. I will give some examples in other domains and some examples in audio. And then I will focus on one specific example for unsupervised source separation using hybrid deep learning. And then hopefully we will have time for questions and exchange after the presentation. So a bit of context and motivation. So we had in the past many work on signal processing and signal processing approach for audio signals. And then there is this domain of machine learning where we can learn concepts from data. And in this domain, there is a growing trend towards developing pure data-driven deep learning approaches, which means that what we build is only using the data. And deep learning are this deep neural network that I will talk a little bit about during this talk. And why there is this growing trend, and the main reason is that you can reach high performances and build state-of-the-art classification algorithm and many other tasks with these techniques. So what is the problem is that the knowledge here is learned only from data. And the main consequence of this is that you have to build a very complex neural network to learn everything from this data. And you need also a huge number of data, and sometimes and often annotated data, to learn this very complex model. So basically the model is over-parameterized, with sometimes hundreds of millions of parameters. And basically, the whole process is working in an overconsumption regime, too complex, too many data, and even worse, what you have at the end, it's a model which is largely non-interpretable or non-controllable. Basically, you build a black box, and it works. It works better than other things, but you're not completely sure why. And this context and motivation is the main goal of my ERC project that Gianpaolo mentioned that will start very soon. And the main goal of the project is to build controllable and more frugal machine listening models based on expressive generative modeling, so models that can generate data. And the approach is indeed to build hybrid deep learning by integrating our prior knowledge about the nature of the processed data in the deep neural architecture. So it's not new, I will say, this concept. It looks like it's an old concept, but and there are some prior work. And for example, here I give an example in physics, where the goal is to estimate the temperature of a lake using a bunch of sensors of data, but also using a physical model, because they have, in physics, very strong physical models to describe and to estimate what will be the temperature of the lake. And they can also combine these physical models with deep neural network using the data in a so-called physics-guided neural network, making the bridge between pure physics-based methods and pure data-driven methods. There are also some work in digital communication or image restoration, and basically they will replace a function, a probabilistic function that estimate the transmitted code from a noisy estimation of the code, and they would replace that by a neural network to estimate this code. And in this very nice paper, they also describe this hybrid deep learning with mainly two big branches. A branch where you use the neural networks to express a functioning of an algorithm, and a branch where the DNN, the neural network, we've learned some parameters of a signal models or of a given models. But of course, this is only one view, and it's a partial view of what you can do with hybrid deep learning. So the question is that why hybrid deep learning is interesting for audio? I think we have a number of reasons why it's interesting. First is because we have good a priori knowledge of the sources. For instance, and we have models for that. I mean, we have built models in the course of history. We have built a number of models in a different aspect of audio signals. So first, we know how we perceive sounds. Well, we have some knowledge of how we perceive sounds. So then we can use audio perception model. We know also, we have some knowledge of how sound is produced. Sometimes we know the instrument that produces sound. We can build physical models of the instrument. And singing voice is one example, because we know the vocal tract apparatus and the way we produce sound. We may know how the sound propagates. We may even know in which room the sound has been recorded. And also we know that signals, audio signals, can be structured in some ways. They can be made as sum of sinusoids. And we know we have experts in the room about the sinusoids. And we know that audio signals, in fact, sinusoids are major components of audio signals. And also, audio requires some specific deep neural network architecture. Because, in fact, if you compare to image, an image, basically, the y-axis and the x-axis are the same dimension. And an object in the image is a compact. All the pixels who are nearby have more chance to belong to the same object. In audio, it's not the case. In fact, here you have a spectrogram, you have frequency and time, and an object, an audio object, for example, here, you have one audio object. Well, it's separated line in frequency, and it's not a dense object in the visualization of the image. And also, there is a time. We have to take care of the time evolution. So then when you do hybrid deep learning for audio, the idea or the goal is to develop novel models for hybrid deep learning, combining parameter-efficient and interpretable audio models with deep neural architectures. So if I use the same drawing of the physics-based neural network, we have this bunch of potential models of audio that we can use, the deep neural network, and we can build hybrid deep learning by hybridizing, I would say, the whole architecture. And also a nice concept is that, of course, and I will give some example, you can build a model just at the input of a neural network, for example, a perceptual model, or a model that will learn features. But you can also use, as it was shown in the diagram of the state-of-the-art, a neural network to learn parameters of a model. But you can even go a bit further. You can embed completely the model inside the neural network, so then it's jointly learned, jointly constrained with the neural network. So what type of model can we use? I will give a few examples of work which touch part of this hybrid deep learning aspect. So we can use a signal model. So it will not be a sinusoidal model, but it will not be too far. And it's a very popular model for audio representation, which is based on non-negative matrix factorization. So what is this type of representation? We have an audio spectrogram of a musical note, which is played from here to here, a second musical note, which is played from here to here, and then the sum of the two notes. And we decompose this spectrogram as a product of two matrices. One matrix will capture the instantaneous spectrum of each node. So one spectrum for the node 1 and one other spectrum for node 2. And the second matrix, H, will basically say which point of time each of the templates are activated in time. Okay, so this is a quite popular model that has been introduced for image, but it's quite popular for audio, and in fact, in particular for source separation, for instance. So what can you do with such a model? You can say, for example, here it's an example where it has been used for audio scene classification. Audio scene classification is a task in which, from the recording, you try to estimate where it has been recorded. Is it in a subway station? Is it in a room? Is it outside? Is it down inside? Etc. So you find the scene in which it has been recorded. So basically here, how it has been used, you have the traditional method on the left, where you have the raw signals coming in. Sometimes you compute some handcrafted features, engineering or manual features. The MFCC have been very popular for that. And then you have the classifier, which will say which class is recognized, so is it inside, outside, and so on. But you can also say, okay, an audio scene, the concept is that an audio scene is made as a sum of audio objects. There is a car, there is a bike, if you are outside, there is noise from cars, there is noise from people speaking, there is maybe reverberation, and so on. So it's made of sum of objects. So then you can compute the spectrogram, compute this non-negative matrix factorization as a sum of basic sound objects, and then use the output of this factorization as new features, as enhanced features for the classification, and you can put any deep neural network to do the classification afterwards. And in this work, what is interesting is that if you use this type of representation, then you can use a simpler neural network and obtain the same performance as if you were going straight with no information, I would say no enhanced information about the signal. So that is one way of doing things. If I stay with the non-negative matrix factorization, there is another concept that can be used, and which leads to the so-called deep non-negative matrix factorization. So the classic NMF, as I mentioned, express the incoming spectrogram as a product of W and H. But if you look at how it works, this NMF algorithm, it's an iterative algorithm. So basically, to solve this problem, what do? You minimize a distance for each time frequency point, so in such a way that it reproduces this factorization of a matrix. So then the reconstruction M hat is as close as possible to M following a given distance. And this, one way of solving this problem is to obtain iterative update rules, because the problem is convex in each of the separated variable H and W. And you obtain a set of two iterative update rules, one for H, one for W, and you iterate until convergence of the algorithm. But then you can say, okay, it's iterative update rules, it's multiplication of coefficients and addition of coefficients. This can be one update of this iterative algorithm can be replaced by a layer of a neural network. And so then you put as many layers of neural network as iteration you want to iterate these two update rules. And you can even think that it's only an iteration on H and you fix the W, but here you update both. But of course, so this works, and it works. You can learn then from data a little bit more, and it works better than the initial algorithm for a fixed number of iterations. The drawback is that the number of iteration is completely linked to the number of layers of your neural network. So of course, it's a limitation in that. And this concept is called and known as deep unrolling, but it has the limitation I just mentioned. Another very interesting work I would like to mention, because I'm going to use that also in the part of the talk, is this concept of DDSP, differentiable digital signal processing, and basically which aims at coupling signal processing models with deep learning for audio synthesis. So here what you see and what is interesting is that you have a model, which is here, which input an audio and try to synthesize an audio which is as close as possible to the input audio. And it solves with using a distance between the spectrogram of the synthesized audio and the initial audio. And it optimized all the parameters of the synthesizer to synthesize an audio as close as possible as the input signal. But what is nice here is that the synthesizer is a parametric synthesizer. So basically, it will encode some parameters. It will extract loudness features. It will extract from an encoder a latent representation and the fundamental frequency of the sound, because it's only for monophonic sound. And then the decoder will generate the harmonic content, the noise content, estimate the reverberation, and synthesize the sound. So what is nice here is that the neural network is not completely a black box, because there is a synthesizer model with few parameters that you can control and generate the sound. And you will see that, so I spent a little bit of time to describe the model, because it's, of course, what is nice in this thing is that to allow this model to work, all the functions need to be differentiable, because learning the network means that you have this distance here between the two sounds, and you do it by a stochastic gradient algorithm where you need to differentiate the different modules that you want to learn. So this is one of the major contributions of this paper, is to build differentiable operators so they can be embedded in the neural network and be jointly learned with the neural network parameters. Another example, which is another possibility of using this concept of hybrid deep learning for audio, is the phase estimation task. So here, what is the goal of the task is you have the magnitude spectrogram of an audio, and what you want to have is a complex magnitude of the audio, because then if you do the inverse Fourier transform of these signals, you will recover a time domain signals, which will be perfect. So basically the problem is that you want the phase retrieval problem is to find X as a complex spectrogram subject that it has the same magnitude spectrogram. And for that, we have a very classic algorithm, which is called Griffin and Lim algorithm. And basically, what it exploits the concept of spectrogram consistency, which says in a short sentence that if you have a spectrogram, it should be, if you have a magnitude spectrogram, it should be the Fourier transform of a real time domain signal. And so then the problem is a little bit different, is that we need to find this complex spectrogram, subject that it has the same amplitude spectrogram, but subject that it's in fact really a Fourier transform of a time domain audio signal. And this is done by Griffin and Lim as an iterative algorithm, the same way as the NMF. So you do by projecting the estimation of your Fourier transform of your complex spectrogram, and you do back and forth going to time domain, and so you have an iterative algorithm. So this is just taking the phase of the current algorithm, and here you do the Fourier transform and the inverse Fourier transform of your spectrogram. And again, here you can use a neural network. So it's used a little bit different than just the unrolling. You just replace one of the iteration PA, PC. You help this inversion, PA, PC, this conversion, by a neural network to improve each of the steps. So it's not exactly explaining the Griffin and Lim's as an iterative algorithm and you replace one layer of a deep neural network by one iteration of the algorithm. You just use a deep neural network to help each step to be more efficient. But it's a nice concept also, and of course it works better than the basic refinelim if you read the paper. Because if you don't show that it works better, then it's difficult to publish your paper, of course. And also, the last example from the literature that I will describe is work, coming from this conference not too long ago. I think it was presented like 2 hours ago. And in fact, it's an example of hybrid deep learning. It's combining ordinary differential equation. Okay, it's a model, physical model, and a neural network to learn the derivative function. And so this virtual analog modeling of distortion circuit using neural ordinary differential equation is a very nice example of how you can also implement hybrid deep learning for audio. Okay, so now I'm going to describe with more details one way of doing hybrid deep learning audio for audio source separation. So audio source separation, music source separation, what is a basic task? So you have polyphonic music. If you use deep neural network, you have a big neural network. You have a database where you have in the database the aligned data from polyphonic music and the individual sources which have been used to build the polyphonic music. And the goal is to recover each of the individual sources only from the polyphonic music. So that's the task. So usually, of course, these models, you share all the drawbacks as I've mentioned in the introduction. So the knowledge here is learned only from the music database. It's complex. You need to have big models to make it work properly. Yeah, and it's also largely non-interpretable and non-controllable. But there is one more limitation, is that you need to have this aligned data. So you need to have a large number of audio signals where you have the complete recording and the individual sources. And of course, this is more difficult to obtain than just audio recordings. So what are we going to do? We are going to exploit this concept of hybrid deep learning, and we are going to use knowledge about the signal. And here, the knowledge about the signal will be obtained thanks to a source filter model, which is, of course, a very old model, but it's an efficient speech production model. So it has been introduced for speech in the 1960s, with the acoustic theory of speech production. And basically what it says that the signal, the speech signal in this case, can be represented as a source signal, that will be the signal emitted by the vocal folds vibration, and which is filtered by a resonator, which is basically the two tubes, nasal tract and vocal tract. And then the spectrum of the output speech is the multiplication in the Fourier domain of the spectrum of the source. So of course here it's very idealized, multiplied by the response gain of the filter, which give the spectrum of the speech for one frame of the analyzed signal. Of course, it's a very simple model. Here it's only a very periodic source with flat spectrum, where in real life, the source coming from the vocal folds is significantly more complex, and you will see that in the model that I will describe, it is a little bit more complex than just a very periodic train of impulses. So now how are we going to do? We are going to follow the same concept of the DSP, but here we are in the polyphonic context. We don't have only one source, we have multiple sources. The idea will be, we take this source filter model, which is a production model, so we are going to exploit the knowledge about how the sound is produced, and we put it directly in the loop, and then we are going to replace the estimated source by the differentiable generative audio models that will synthesize, and for each of the instruments, that will synthesize the target audio. We add all the sources, then we have a synthesized music, and then similarly, we compare, we estimate, we learn the model, all the models, with only comparing the synthesized music with the polyphonic music in this optimization process. And of course, this has many advantages. Here, it really implements the idea of the fact that the model is at the core of the neural network. Also, what is nice is that the source separation is done by synthesis. And if you synthesize a target source, of course, it's nice because you have no interferences from the other sources. You synthesize only the target source, so which is nice. And also, what is very nice, maybe the main advantage, is that you do the learning only from polyphonic recording. There is no need of the individual sources at any point in time in the learning process. And this is nice. And also what is nice is that you have models. You have models with a few control parameters. Source filter models, it's only a few parameters. Then you have capabilities of sound transformation. So you can change the timbre, you can change the melody of the voice, you can change the lyrics, you can do translation, you can reharmonize, and so on and so on. Okay, so this is the idea, this is the target. Now, maybe a little bit more details if we can do or approach this dream. Okay, so what we have done so far is preliminary work. Preliminary work on source separation on the typical aspect of choir singing. So choir singing, then we still have our source filter models, but we have always the same source, always the same model. We don't need to have a model of piano or guitar and so on. We have 4 times the same model. And also it's a complex task because it's not easy to do source separation where we have sources of the same type, same timbre. It's a very complex task, but it's a very nice idea for working on this problem. So here is a whole system, and again we only work from the synthesized and the polyphonic music. We do the comparison. So choir singing separation. So the model, if I go into a little bit more details, is the following. We have to predefine the number of sources, and because we did not succeed to build the models where everything is learned at once, we separated the problem in 2. First, from the mixtures, we estimate all the fundamental frequencies which are present in the signals using multi-pitch F0 estimation algorithm, and there are a bunch in the literature, and some are very efficient. And then we built a rather simple, rudimentary F0 assignment to each of the sources. So then all the rest of the model knows that this fundamental frequency goes to source 1, this other fundamental frequency goes to source 2, and so on. So basically, we are in a framework of F0 informed audio source separation, even if the F0 information is obtained by directly estimating it on the signal. It's not known, it's not given by score or whatever. So the whole model, which is learned at once, is everything but the 2 multiple F0 estimation, which is taken on the shelf from an existing algorithm to estimate the fundamental frequencies. Okay. So now let's describe what is a parametric model. The parametric model, as I mentioned, is a source filter model. The source is a vibration of vocal folds, and the filters is a resonance of the vocal and nasal tracts. So basically, it can be represented like that in a very simple form. The spectrogram of the source, the spectrogram of the filter, and the resulting voice spectrogram of the voice signal. So this is nothing new compared to what I presented before in the source filter model. But now I'm going to give a little bit more details about the excitation model and the filter model, which are a little bit more elaborated than just what I described before. So here you have the parametric source model, and it's very close to, well, it's exactly the same as a classic and harmonic plus noise model, I would say. But you have a number of coefficients to tune the harmonic component and the noise component. So on the top, you have the harmonic component of the source. So you have the F0 fundamental frequency trajectory, which comes from this multi-F0 estimation algorithm, followed by the F0 assignation to each source. So then you have, for each source, you have a trajectory of fundamental frequency. Then you have a gain that will say at which strength this harmonic content is present. You have a filter. So this is an invariant filter, and basically it provides the spectrum of the source. And in fact, I mentioned in the theory that you had a very flat spectrum for the source. In practice, for singing voice, you have kind of a better models will be a decay with frequency of the spectrum of the source, which is represented here by this filter. And then you generate the harmonic component, because all harmonics are multiple of the fundamental frequency, and you have the harmonic content of the source. Then for the noise, it's also quite simple. You have white noise. You also have an invariant filters, because we want the noise to basically cope for the high frequency component of the signal and not have too many noise and the low frequency, which correspond to the physics. Even if you do unvoiced speech, for instance, you will have noise emitted directly at the vocal folds, so then you will have noise also in the low frequency. And maybe for the sounds such as F, where you emit the sound just at the lips, you emit a pure white noise with no filtering. But for most of the sound is filtered and by the vocal tract, and then it's mostly in the high frequency. So this is the role of this invariant noise filter. Then you have noise gain, the same as gain for the harmonic. But you have two coefficients. Maybe we could have get rid of one. And then this is the noise part. We addition the two, and this makes the excitation source. For the filter, we could have used a typical linear predictive model, which is very common in audio coding and audio signal representation. But in the early experiment that we did, it could happen that the filter was not that well estimated, and in fact we could have estimated filters which were unstable, which is very bad for synthesis, of course. And so then the idea came to go back to what has been introduced for audio coding, which are the line spectral frequencies. I'm just going to say a word about them, but which can represent the filter, but with one of the biggest advantages is that the filters you obtain is always stable. So basically, when you do a linear prediction coefficient, linear prediction analysis, you try to predict the signal from a number of previous samples that you have of the signal. So this is the first equation. And then if you rewrite the equation and you go to the z, you do a z transform of the equation, you obtain the expression, the following expression, that the signals can be expressed by the excitation filtered by a filter. And of course, what we are interested for a synthesis approach is 1/AZ, okay? And then to estimate the AI coefficient, you have a number of algorithms, such as the Levinson-Durbin, for example, based on Levinson-Durbin iteration. And but so the LSF, what are the LSF? Is that it's a different way of seeing the same problem. You go towards two auxiliary polynomials, and you will look for the zeros of these two polynomials. And one characteristic of the zero of these polynomials is that they are on the unit circles. So you can see here is a representation, and they're also very informative about the resonance of the filter. So if you look at on the unit circle, you have the zeros which are alternating between F1 and F2, which are here. And in circle here, you have the 0 of AZ, the original. And you can see that two spectral pairs correspond to one of the 0 of the original filter. And in fact, if you look at the spectrum, or the gain of the relative gain of the corresponding filter, 1 over AZ, you have in black the spectrum that you obtain from LPC, from linear predictive coefficient, and you have in blue the position of the 0 of the LSF, and you can see that this LSF can be very well represented, can be very representative of the spectral envelope of the spectrum, of the spectral gain of your filter. And the advantage, if you estimate the line spectral frequencies, the filter 1 over AZ will always be stable, because you have very simple ways of converting LSF to the AI coefficients. So then to obtain this 1 over AZ filter. Well, it's a detail, but it's since it's a specificity of the implementation, and in fact it was not working through the linear predictive coefficient, I think it was nice to precise that. Okay, so now we have the model. The thing I have not described at all is what is the spectral loss. So what do we optimize between the incoming spectrogram and the synthesized spectrogram? It's a multi-scale spectral loss. And basically, this is a cost we try to minimize. So it's the distance between the incoming and target spectrum, and in normal amplitude and in basically close to dB in log scale. And we do that at multiple scale, so then we have multiple resolution of the different spectrograms. Okay. Some people like to see exactly the details about the neural architecture, so I decided to show this diagram. What is nice to see here is that you have in blue the information which is given externally, which really highlights the fact that it's not optimized within the rest of the model, which is the F0 coefficient. The F0 that you give for each of the source J, so you have J trajectory of F0. And then you have in gray all the deterministic or algorithm which are deterministic of the which are not learned by the different by optimizing the loss. And in green you have everything which is learned by optimizing this cost that I have described. So you learn, of course, all the parameters of the neural network, and what you obtain is everything which is white, and this is everything that is needed for your for the model. So you obtain latent mixture representation, you obtain harmonic amplitude, noise gain, noise filter magnitude, you obtain the nice spectral frequencies here that you convert to the AK coefficient, you obtain the noise filter, and so on. Wow, I should accelerate. Okay. So the good, yeah. Then there will be no time for questions, but I will accelerate. So I mentioned, yes, it's a very good. The model is very nice because we do synthesis. Here we synthesize the source, okay? And this is one of the major advantages. In fact, we try also another aspect, is that instead of synthesizing the source directly, we use the spectrum of the synthesized source to filter, using Wiener filtering, the mixtures using this softmax, basically the spectrogram magnitude of the target synthesized source. So this is not exactly the same as synthesis because it takes the phase of the original spectrogram. And so this, we call it by filtering. It's a more traditional way of doing source separation. And unfortunately, doing the source separation using this mask approach is better than doing the synthesis approach, which is a drawback and a disappointment because the claim was that the synthesis is better. But But we still use synthesis to build the mask, so we're not completely dead. Okay, so the result, the good thing with this approach is that it's unsupervised because you do not lead the aligned signals from the mixtures and the separated signal. But if you use this information of having the signals and the aligned signals, it's called supervised approach. But this unsupervised approach is almost as good as the supervised approach. You almost have no drop in performance, which means it works. The unsupervised approach, this hybrid deep learning approach, works because you don't need the information of aligned signals, but it works almost as the same. So I've not mentioned the matrix, but this matrix is a typical metric to evaluate the quality of source separation, or the quality of source reconstruction. Another thing which is important to notice is that there is almost no drop of performance if you use much less data. So basically, here is the unsupervised models with the full training data, and here is the unsupervised models with only 3% of the training data, and you have almost the same performance. And here is the same when the model is supervised, which is good. And so the claim is that we need much less data it seems to be true. And what is even nicer is that if you use a baseline model, so it's big models, which is trained in the same way using the F0 information from the F0 estimation algorithm, if they use much less data, then their model drop. Is that the fact we embed a model of production helps to use much less data to keep the same type of performance. And I think this is a very nice outcome of this. It's a very good promise for the future. So now let's listen to some sound. So you have a link here. In the first few slides, I give also the link to the paper. It's a paper which is only on arXiv for now. And you have a code also here. And I will not go to this site because it's remote, and I was not completely sure of if I will have a link, but I have a duplicate of the model of the site on my computer, so I am going to be able to play a few sound. So let me, since I'm already over time, I will only play one example. So here it's an example with 4 sources. So the first thing I will play is that if I listen to the resynthesized mixture from the model, we can see that it will be very close to the incoming mixture. So the model is able to reconstruct the synthesized sound. In fact, since it optimizes the distance between the synthesized mixture and the incoming mixture, it's nice. But is it capable of reconstructing the individual sources? So now let's listen the target soprano source. And what the algorithm is successful to estimate. Maybe we can do the same for the bass. And if we compare to the synthesized source, which I said is a little bit less good, you hear some artifacts, or this is estimated by Wiener filtering, and this by synthesis. Okay, and then there is all the other, so it's not bad, but it's slightly less good. And then you have a number of all the different models that, for example, if you compare with the UNet model with the baseline, for the source, for example, the soprano. So it's slightly less good even with the full training database, but in fact, if you use a very small database, it degrades a lot. Okay, and the last example I'm going to play, so there are many other examples on the site. The last example I'm going to play is that I mentioned what I claimed, that it's possible to modify the audio signal. So I'll just give you one example of modification. This is the original mixtures. The resynthesized mixture. And the modified one. It's quite simple to do, and I guess it could be better done, but it's a very simple modification of the signal. Okay, and some takeaways from this work. I mean, of course, only a small amount of data is needed, so this is clear. Filtering the mixture is better than synthesis, which I mentioned is a bit disappointing. That we have here differentiable all-pole filters, and the parameterization of the mixtures is provided, so then we have many capabilities of changing the sound. Okay, so to conclude, what I wanted to highlight is that there is quite a high potential for hybrid deep learning, which I'm happy, because now I will have to work on that for the next, the next few years. And what is clear to me is that this type of approach brings interpretability, controllability, and explainability. And that, in fact, you have a models which becomes controllable by human understandable parameters, basically by, if you have understandable, efficient signal models or perceptual models, then you will have a model which is interpretable in these terms. And of course, it brings also new and enhanced audio capabilities, modification, transformation, and so on. It also, it's a consequence, but it's not really the main goal, but it's a consequence, is that we should gain several orders of magnitude in terms of complexity of the model, but also complexity of the number of data that you need to use. And I think the first preliminary work really shows that. I mean, using 3% of the data instead of 100%, it's almost 2 orders of magnitude, and it's almost the same performance. So, and basically, it should contribute also to have a more resource-efficient and sustainable AI, which is a problem of major importance in today's AI, and to have an AI which is also accepted by society and by everyone. Okay, so that's all what I happen to say.
Is this on? Do you have plans to extend this model to like stuff which is not being able to be synthesized with like a normal source filter model, like drums or non-harmonic content?
Yes, I think a direct extension is for audio source separation will be to combine with other type of models, to combine with other sources. And also, as I mentioned, one of the drawbacks of the current model is that we have to, I mean, to make it work to that point, we had to estimate the fundamental frequency. We can imagine that we can have a model of fundamental frequency which is embedded also in the models, maybe with a few parameters. So then it's not a big models, big black box that we include. But yes, absolutely.
Thanks. Maybe a bit of a meta question for your whole kind of approach there. So I'm wondering about the learnability, so the quality of your loss surface. So the one idea would be that, yeah, if you have a model, then you have less parameters, so you have less to learn, but it might be also that these parameters become much harder to learn, right? Do you have any idea on kind of, is there some guarantee that it stays learnable, or whether it makes it? Do you have some kind of general idea on what this means to include these models there?
I think it's a very good question. It's an excellent question for which I have no answer. That's why it's a very good question. Now, more seriously, yes, no, there is no guarantee. I mean, in the work that has been presented this morning with ODEs, it's also exactly that. We want to estimate, to learn something in a different way, but there is no guarantee that it works. And in fact, for the LSF here, it's the same. We know exactly that LSF will be zeros on the unit circle, but the only constraint that we give to the algorithm is to represent 0 on the unit circle, which are ordered. And the algorithm will find the best position of this 0 on the unit circle to represent the signal. So it goes a little bit away from the meaning of the LSF, but in fact, it's one of the beauty of this machine learning from data is that it can learn very complex, and this deep learning, it can learn very complex relationship between data, between input and output. And this is what makes it powerful. But if you ask me what is the shape of the space that is learned, well, it's a field of research also, but it also can be also a constraint to be used and say, okay, I mean, one of the nice idea of this hybrid deep learning is that to say it limits the space of solution, but it doesn't say that this space of solution is organized in a very compact and dense way. And in fact, I'm sure it's not, especially if the model is very complex especially if the parameters of the model are very complex to estimate and very nonlinear. But thank you for the question.
Hello, thank you for the talk. Because my other questions were asked, I was just going to ask with regards to parameterization, just in terms of using LSF and other kind of like derivatives of LPC, like did you guys ever look at like using like the reflection coefficients that would come from LPC and that would be easily constrained and stuff like that? And can you comment on performance, if so?
Okay, I'm not completely sure of the answer. I think, because of course I have to mention that the work was tackled by Kilian Schulz-Forster, the PhD student who worked directly on that work. And if I remember correctly, the path of the work was exactly that. So AI coefficients, then there was this problem of unstable filter, and say, okay, look at the reflection coefficient, but we move rapidly with the LSF because they were a very easy way to predict them with the neural network. And we had also this guarantee that it was stable, and that's why we move rapidly. So we did not spend too much time with the reflection coefficients, which in fact are very interesting because the reflection coefficients can be transposed to a discretization of the tube, and as it's used in linear acoustic. But yeah, no, I think it's a good, but we touched it, but we did not explore it too much, I would say.
Thank you very much. I like the approach of hybrid machine learning models very much, and I would like to add some auditory processing into the loop. For example, in order to get a better estimate of what's going on the perceptual side. But most of the auditory models are not differentiable. How would you cope with this problem?
So this is the basic problem. Is that, and in fact, the contribution of this DDSP paper, this differentiable digital signal processing, is typical ways of expressing differentiable function of non-differentiable at the basic, non-differentiable model. So there is tricks that you can use to estimate or approach the derivative. So that you can use for that, for the perceptual model. And you can maybe also, you can maybe simplify your auditory model in a way that it's more differentiable. And the third way is that you can use it as a, let's say, as an additional constraint in the loss. You could just say, okay, you should not follow completely the perceptual models, but you should have at least some basic knowledge, very simple, that you impose on your representation. For example, if I take one example, if you want to include the fact that the hearing system is more or less following mel scales and linear scale in frequency, then you say, okay, in the distance, well, in this way, I mean, in this work, it's used in a very basic way, but it's used in the loss, where you combine a loss on the spectrum and on the log spectrum. So you could claim that this is an aspect of a perceptual model which has been embedded in the model. A very simple way and very rudimentary way, but it's another possibility. But finding a derivative approximation of your model, this is, I would say, the main path, but it's not always straightforward.
My question is, you assume that there is one model that humans would use, it seems, and then you use deep learning to improve, let's say. But how about finding several, I mean, humans have developed several models or algorithms, and then have a deep learning of which model would be better, and then do the optimization, let's say, with further deep learning. Is that something that you're considering? It's a contorted question, but...
Yeah, I'm not sure I've well understood the question. Do you mean using the deep neural network to find which model is better?
Yeah.
So if I rephrase your question, just to be sure that I well understood, you have a model 1, a model 2, a model 3, a model n, and then you have a deep neural network that say, okay, that optimize a loss, and it will either select one of the best model for each of the tasks, or it will combine the output of the model for doing the task. So yes, this is a classic, I would say, in machine learning. It's what is called fusion of model, no? Or is it...
I was not really thinking, you put the fusion in, I was thinking of selecting the best one, but so that the machine then further improves. So once the model, I mean, it tries all the models and then tries all the improvements with each model. I was not thinking.
It's very nice, yeah. I think it's a very nice idea. In fact, yes, so it's, it's extension of selection or fusion, because selection is kind of a sub-problem of fusion. But in fact, the nice idea is that the deep learning can improve each of the model. So it goes further than the fusion aspect, where fusion, usually, you combine the output of several models, and you can show that if you do fusion, it's always better than the best of your model. But here you can do even better, that you can improve each of the model, or you can even select the model which has the best capacity of improvement, which is very nice concept. I like that.
Yeah, with direct relation to the previous question, that's actually something that I'm currently working on.
I don't know where is the question coming from.
Here.
Sorry.
Hi. Sorry. So yeah, I'm currently working on hardware-aware neural architecture search, trying to build a search space out of different signal processing components and automatically composing a neural network architecture out of this using evolutionary algorithms, basically, which is very similar to what's been proposed now. So I'm trying to use artificial intelligence to build a neural network with signal processing components that are most fit to the task. So that's currently what I'm working on.
Yeah, so there is no question.
I just
no, I'm joking.
wanted to say that this is the thing.
No, but I'm joking, but I will be very interesting to talk to you. I think it's very interesting. And in fact, it's also one of the ideas that I would like to study. And it reminds me early work from François Pachet and his team on finding, on combining elementary signal processing function So I'm not sure it was using evolutionary algorithm, but he was searching for elementary signal processing function and combining them, making functional function by searching a huge space. And in fact, it's a very, I would not say that it led to very successful new representation, but it's very interesting, and the function that was found had sometimes a lot of sense because it was recovering some of the functions which were manually tuned. So I think it goes into that direction, and of course with the power of deep neural network and finding the architectures of neural network that can well combine signal processing modules, I think it's a very interesting path. So thank you for mentioning that.
Can I ask one more, maybe? I just wanted to ask that on the slide you have J sources, and is J set in advance, or is it also something that's learned during training?
Okay, so in this work, it's set in advance. So as I mentioned, there is two limitations in this preliminary work, is that F0 is not learned jointly. And in fact, we have done some few other study to show to see how much the model is fragile to a weak estimation of the fundamental frequency. And in fact, it's not too fragile. But of course, if you have mistakes in F0 frequency, you will have mistakes in the sources. And the other problem is that, I mean, it's not a strong limitation, the number of sources, but we fix the number of sources in advance. So then we know. So on the website, you have example with 2 sources and 4 sources, but for both cases, we give to the algorithm, now you have 2 sources, and now you have 4 sources. But it's not a major problem, because most of the use cases, you know the number of sources. I mean, if you take a quartet, well, you know a quartet, if there is a 5th source, is that there is some problem with the recording process.
Okay, thank you.
Okay, hello. I think we have one last question, and I think you asked it first.
Hello. Yeah, so I noticed the commonality across these models, these model-based audio signal processing models. The loss was a spectral loss, STFT loss, most of the time, I think. And you've kind of said a lot. We can use models of auditory perception, hearing to facilitate training. And I was just wondering, yeah, the STFT loss tends to work in a lot of problems, but are there any problems where perhaps more perceptually relevant signal processing models are like really necessary? I mean, a simple example is I found for some problems like even a frequency axis which is not linearly spaced improves the audio quality results. Yeah.
Okay, yes. In fact, so since we are on this slide, so then it can help me. In fact, one extension of this work is to change the loss. Okay. In this work, we did not explore a lot the different losses, and this is a loss which is proposed in this paper, not in this paper, in the DDSP paper. So we did not change the loss, and basically it's yes, it's a basic loss. What it captures from the audio signals, what I mentioned, is that it's important to have the log, because in fact we are sensitive to the logarithm of the spectrum more than the direct spectrum, and we also would like to see audio objects which are a different resolution, because we are also capable of doing that when we hear sounds. But it's not at all a perceptual model. You can put here a model which is much more sophisticated, which in fact is a pure perceptual model. You want to reconstruct a synthetic mixture which is perceptually equivalent to the incoming, but not in terms of SNR, in terms of perception. And in fact, I don't know if it will work better, but it will be more satisfying in terms of perception.
Yeah, I mean, these examples you've shown already sound like very perceptually similar to the ground truth. So maybe not with this problem, but I'm sure other problems that could be more challenging.
Yeah, I'm sure. Yeah, it's a direct extension of that, and it makes sense. It makes full sense to do that.
Okay, so there is time for another clap.
Thank you.